If you enjoyed making electrical circuits, then you have definitely soldered before. But as you can see, soldering can produce quite a bit of toxic fumes. Obviously, wearing one of these isn't an elegant solution. So in this video, I am going to show you how to repurpose an old 80mm solder fan to make a USB soldered fume extractor, with its main feature being having a flexible arm that allows you to suck in fumes from a convenient direction, and have its power be fully adjustable. Here are the components you'll need for this project. As for always, all the link and part files are in the description. The first thing you'll need will be a 80mm by 25mm 12V computer fan. I recommend selecting a fan with a power rating of at least 3 watts. To power the fan, I am going to be using this XL6009 boost converter circuit. Other components you'll need is this 2A switch, a small 10kΩ potentiometer, a micro USB female connector or a USB cable, a 300 to 500 ohm resistor, a small 3mm green LED, 16 gauge steel wire, 1/4 inch inner diameter vinyl tube. Finally, you will need to 3D print all the files in the description. The maximum output voltage of the boost converter is well over 30 volts. This is more than enough to destroy the fan. So the first step is to set a custom voltage range for this boost converter. In this case, between 5 and 12 volts. To do this, first connect 5 volts to the input of the boost converter. Then, using a voltmeter to measure its output, turn the potentiometer until the output voltage reaches 12 volts. Now turn the boost converter to its backside. As you can see, only the right 2 pins are connected to the rest of the circuit, so I will only measure the resistance between those 2 pins. When the output voltage is at 12 volts, the resistance between those 2 pins are 2.9 kiloohms. Write it down somewhere because we will be using these numbers to compute the value of the resistors later. Now decrease the output voltage of the boost converter to 5 volts, and then measure the resistance between the 2 pins again. In this case, I got a resistance of 1.2 kiloohm. The difference between 5 and 12 volts on the boost converter in terms of a resistance is 1.7 kiloohm. So at this point you may be asking, how do we get a 10 kiloohm potentiometer to behave like a 1.7 kiloohm one? And the answer is that we can connect another resistor in parallel. The general formula of 2 resistors in parallel looks like this. Since we got a 10 kiloohm potentiometer, we can plug in 10 as the first value. And since we want to get a resistance of 1.7 kiloohm, we can set this as the answer. Solving for the other resistor, we got a resistance about 2 kiloohm. Now we can connect another 1.2 kiloohm resistor in series to adjust the value to our maximum 2.9 kiloohm. And from this, we can derive our final resistor schematic. To apply this modification, first desolder the potentiometer that is on the boost converter, and adjust its value to 1.2 kiloohm. Now cut off one of the pins on the edge of the 10 kiloohm potentiometer, and solder a 2 kiloohm resistor across the other 2 pins. And then solder the 1.2 kiloohm potentiometer in series, and connect it back to the boost converter. And as you can see, after this modification, we have successfully set a limit on the boost converter. The voltage should now only vary between 5 and 12 volts. The next step is to make the input circuit. First, solder the ground wire from the USB female connector to the ground of the boost converter's input. Next, solder the positive wire from the female connector to the switch. Then, solder a 500 ohm resistor and a wire to the output of the switch. Connect the wire to the input of the boost converter, and then connect an LED between the resistor and the ground. Now it is a good idea to test the circuit to see if the LED works and if the fan is controllable. Additionally, you can add a small heatsink onto the chip of the boost converter, but this is optional. To make the arm, First, insert a U-shaped wire into the holes at the top of the electronics enclosure. And then, insert long wires into each of the holes. Solder the wires onto the output of the boost converter. The next step is to insert and glue all the components in place. And then secure the lid in place with 3 M3 screws. Now cut 2 vinyl tubes to the length you want for the arm, and push them into the electronics enclosure. Then, insert the wires and tubes through the 3D printed fan bracket, and twist the wires at the end to secure them in place. And then solder the wires to the fan. Make sure you pay attention to polarity. Slide the fan into the 3D printed case, and close it using the bracket. Secure the bracket in place on each side using short M3 screws. The next step is to get the activated carbon filter, and trace the shape of the 3D printed intake onto it. And then cut out the filter and stick it onto the inside of the intake. Slide the intake onto the fan, and secure it in place with an M3 screw. The final step is to make the base. Simply slide in the base fins like so, and then secure the electronics enclosure onto it with 2 M3 screws. And after this, the project is finally complete. All you need is 5V USB input, and then flip on the switch. As you can see, the power is adjustable between 750 and 100 mA. And even on low power, the solder fumes can be extracted from 10 cm away. And this is it for this project. I really hope you enjoyed it. And if you did, please give this video a like and consider subscribing to my channel. If you got any questions, feel free to ask them in the comments. As many of you can see, this is the first time I've done voiceovers for this channel. Should I stick to this format, or revert back to the music with subtitles? Please write your feedback in the comments. Also, as many of you eager to know, yes, I have completed the 18650 Power Bank 2.0, but right now it is undergoing extensive testing, so I can confirm that there are no design flaws. This way, when I release the video to the world in July, I can be sure that I got a good design. Thanks for your patience, and as for always, thanks for watching.